AQA GCSE Chemistry, Hydrocarbons. So I'll take you through crude oil and the basics on hydrocarbons and then alkanes before the properties of hydrocarbons and how that is related to fractional distillation. Try and participate, taking notes, completing tasks, skipping ahead if you wish, replaying slides as is best for you. The AQA specification has a very simple outline for the formation of crude oil. In ancient seas 200–300 million years ago, and are originating as biomass, principally plankton in the oceans, which falls to the floor as ocean floor as a sediment. Layers of mud form on top, then layers of rock form on top of that mud. Through unknown processes, the plankton are converted into oil, which is now found in those rocks. Because this is a very ancient process, of course, crude oil is a finite resource. It is not being replaced. So crude oil is a mixture of molecules called hydrocarbons. So here are some examples: methane, propene, benzene, carbon, the black atom, hydrogen, the yellow atom. Again, black and yellow for carbon and hydrogen, different representations, or we can see a benzene structure with element symbols. As we can see, the hydrocarbons are composed of hydrogen and carbon. We've got yellow hydrogen, black carbon, or symbols for hydrogen and symbols for carbon. A key word is needed in this description: only. So hydrocarbons composed of hydrogen atoms and carbon atoms only. Now at GCSE you meet just a few examples of the many families of carbon compounds that are existent in the natural and man-made world. You'll meet alkanes and alkenes, but you won't meet benzene, which is an A-level or is a member of an A-level family or homologous series. All right, so have a look at these four diagrams or representations. What is the molecular formula of methane, of propene and benzene? Stop the lesson, write down the formulas, come back to check. Okay, so to restart, methane, 1 carbon, 4 hydrogens, so we would write that in this way. Propene, 3 carbons and 6 hydrogens, and if you count up here, benzene, 6 carbons, 6 hydrogens. They're all hydrocarbons, they only contain hydrogen and carbon atoms. So most hydrocarbons in crude oil are members of a homologous series, the alkanes. So let's look at the first members of the alkanes. We've got methane, ethane, propane, butane, and pentane. I've given you the molecular formula. From that molecular formula, can you work out a general formula? Pause, come back if you can do it. Okay, so the general formula is written as not as a number 5, but as an unknown number n. And if we multiply 5 by 2 and add 2, we get to 12. So the numbers of hydrogens is 2n plus 2. Now, these first 4 members of the alkane homologous series follow the sequence 1 carbon, 2 carbons, 3 carbons, 4 carbons. Can you work out the molecular formula for each in turn? Stop the lesson, work out the molecular formulas, come back to check when you are ready. Okay, so I'm going to reveal. Methane, n is 1, so 2n plus 2 is 4. N is 2 for ethane, so 2 times 2 plus 2 is 6. 3 times 2 is 6 plus 2 is 8, and 2 times 4 plus 2 is 10. You are expected to remember the names of these homologous series. Can you name this alkane? Okay, so the name of the alkane is, of course, propane, C3H8, if you add up the carbons and the hydrogens. Which of these formulas is an alkane? One of those three is an alkane. Which one? Okay, well, C3H6 is not an alkane. It doesn't follow this general formula. C6H6 is not an alkane. It doesn't follow this general formula. But 2 times 8 plus 2 is 18. So C8H18 follows this formula. C8H18 happens to be called octane, is an alkane. Okay, so a very simple exercise. If it's not necessary, skip ahead. Otherwise, pause the lesson and can you name the first 4 alkanes? Here are their molecular formulas. What are their names? And what is the general formula? Stop the lesson, speak out or write down your answers, then come back to check. Okay, so methane, ethane, propane, butane, you are expected to recall those names. The general formula, CnH2n plus 2, again, expected recall. The properties of hydrocarbons. These depend on the size of the molecule, or in other words, the number of carbon atoms in the formula. So let's just look at some examples of small molecules, CH4, C2H6, methane, ethane, and then larger molecules, C20H42 and 2246. These, of course, are all alkanes. So we've got to consider the trends that exist between the properties of small molecules and large molecules. So that's the key idea. One of which is boiling point. Low boiling point, high boiling point. Large molecules have high boiling points. There's a trend from low boiling points to high boiling points. You are expected to recall that. The explanation lies in the strength of intermolecular forces, which we'd discuss or have discussed in a different lesson. We've also got viscosity, that is how thick or how runny a liquid is. A low viscosity is a liquid that is watery and runny. A high viscosity is a thick, sticky liquid. There's a trend from small molecules to large molecules, low viscosity to high viscosity. So large molecules have high boiling points and are thick and sticky. Finally, flammability. Small molecules are highly flammable. Large molecules are non-flammable or less flammable. So, small molecules are more useful as fuels. They've got low viscosity, they're going to flow around, for instance, a car engine, and they're highly flammable. The opposite is true for large molecules. These trends are expected to be recalled and used as explanations. A major use of alkane hydrocarbons is their exothermic combustion. They combust in excess oxygen, so there's a plentiful supply of oxygen called excess to form always the same two products, water and carbon dioxide. As long as you have excess oxygen, the products are always water, H2O, and carbon dioxide, CO2. Now, you may have seen this demonstration set up in your school laboratory. Here is a wax candle, a hydrocarbon with large hydrocarbon molecules. It's combusting. There's a pump pulling the gases from the candle through these two boiling tubes. In the first boiling tube, a clear liquid condenses. That is the water. In the second boiling tube, there's a solution, a test solution, lime water, and this turns milky, and that of course says that the second product of combustion of the wax candle is carbon dioxide. So water collects here and is evidence for carbon dioxide in that it turns lime water milky. Now, where did the water and the carbon dioxide come from? Well, of course, in a hydrocarbon, you have carbon and hydrogen, and we say they are oxidized to form carbon dioxide and water. But what definition of oxidation is being used to explain this statement? Okay, well, oxidation can be thought of as the gain of oxygen. So carbon in the hydrocarbon fuel gains oxygen to form carbon dioxide. As long as there's excess oxygen, it will always be carbon dioxide. The hydrogen in the fuel gains oxygen to form water. Combustion reaction equations need to be balanced. So let's look at one as a model. C3H8, propane and oxygen, carbon dioxide and water. Have a go at balancing that, see how you do, come back to check in a minute. Okay, so I'm going to restart. So C3H8, we've got 3 carbons, therefore 3 carbon dioxides. That is the key to the carbon dioxide number, how many carbons. We've got 8 hydrogens, therefore 4 waters. The key to the numbers of waters is how many hydrogens in the hydrocarbon. So 3 CO2, 4 H2O. Now we need to balance for oxygen. We've got 3 O2, that's 6 atoms, and another 4 oxygens makes 10 atoms on the right-hand side. So we need 5 O2 molecules. Each oxygen molecule has 2 atoms, therefore 5 times 2 is 10. We are now balanced 10 on the left, 10 oxygens on the right. Here's butane. Balance that combustion equation. Stop the lesson, come back to check when you are ready. Okay, so 4 carbons, therefore 4 carbon dioxides. 10 hydrogens, therefore 5 waters. Now the oxygen, 4 times 2 is 8, plus 5 more oxygen atoms, so that makes 13. But we don't have atoms on the left-hand side, we have O2 molecules. Each molecule has 2 atoms, so we need 6.5, 13 over 2 oxygen molecules. Now, you'll see that written in textbooks very often, either in this form or multiplied through by 2. So we get rid of 13 over 2 to become 13, but that means we need 2 butanes and producing 8 carbon dioxides, 2 times 4, and 10 waters. 2 times 10 is 20 hydrogens, 10 waters. Let's have a look now at fractional distillation. Fractional distillation separates the hydrocarbon mixture in crude oil into fractions, that is, groups of molecules containing similar numbers of carbon atoms, that is, similar size molecules. Here's a typical diagram of the setup. The first step in a description of crude oil fractional distillation is that the crude oil is heated to evaporate. The vapors then enter the fractionating column. At the bottom of the column, the temperatures are high, that is, it is hot. At the top, the temperatures are low, it is cool. So we have a temperature gradient going up the fractionating column, hot to cool. Now the hot vapors enter the column and rise in the column. As they do so, they cool and condense, so two key words in any exam answer, at their boiling point. Each of these groups of molecules have different boiling points because molecules of similar size, for instance those in the diesel oil fraction, will condense at the same level in the fractionating column, that is, condense at the same temperature, because there's a relationship, if you recall, between boiling point and molecular size. Increase the size of the molecule, increase the boiling point. So molecules that condense at the same temperature have similar sizes. So similar size molecules are found in each of these fractions because they've got similar boiling points and therefore condense at the same point in the temperature gradient, hot to cool. Of course, this reflects a trend. The fractions at the bottom will have large molecules and the fractions at the top will have small molecules. Obviously, there's a trend between the two. Crude oil in itself is not a useful material, but the fractions produced from fractional distillation have many everyday uses, and many other everyday materials are manufactured from them using different processes. So the first most obvious use of these fractions is as fuels. The petrol cars will use petrol, larger vehicles will use diesel, so these fuels all have different contexts for their use. There are other specific products you are expected to know about. For example, solvents. For example, lubricants for the car engine. For example, detergents for washing up liquid. For example, polymer or plastics to make containers. So these 4 specific products are expected as knowledge in the AQA specification. Okay, so find some problems on this topic. Your textbook's a good source, and obviously exam board past papers. Complete a number until you are confident. At that point, move on to another lesson. If you found this lesson helpful, please recommend it to a friend. Please like, and if not inconvenient, please subscribe. Thank you.